A smoke detector is a device that senses smoke, typically as an indicator of fire. Commercial security devices issue a signal to a fire alarm control panel as part of a fire alarm system, while household detectors, known as smoke alarms, generally issue a local, audible or visual alarm from the detector itself. Smoke detectors are housed in plastic enclosures, typically shaped like a disc about 150 mm in diameter and 25 mm thick, but shape and size vary. Smoke can be detected either optically or by physical process. Detectors may use either, or both, methods. Sensitive alarms can be used to detect, and thus deter, smoking in areas where it is banned. Smoke detectors in large commercial, industrial, and residential buildings are usually powered by a central fire alarm system, which is powered by the building power with a battery backup. Domestic smoke detectors range from individual battery-powered units to several interlinked mains-powered units with battery backup. If any unit detects smoke, all trigger even in the absence of electricity. As of November 2013 update, it is estimated that smoke detectors are installed in 93% of US homes and 85% of UK homes. Roughly 30% of these alarms are estimated not to work, due to excessive age or lack of working battery. The U.S. National Fire Protection Association estimates that nearly two-thirds of deaths from home fires occur in properties without working smoke detectors. History. The first automatic electric fire alarm was patented in 1890 by Francis Robbins Upton, an associate of Thomas Edison. George Andrew Darby patented the first European electrical heat detector in 1902 in Birmingham, England. In the late 1930s, Swiss physicist Walter Jaeger tried to invent a sensor for poison gas. He expected that gas entering the sensor would bind to ionize their molecules and thereby alter an electric current in a circuit in the instrument. His device did not meet its purpose. Small concentrations of gas had no effect on the sensor's conductivity. Frustrated, Jaeger lit a cigarette and was soon surprised to notice that a meter on the instrument had registered a drop in current. Smoke particles from his cigarette had apparently done what poison gas could not. Jaeger's experiment was one of the advances that paved the way for the modern smoke detector. In 1939, Swiss physicist Ernst Mayr devised an ionization chamber device capable of detecting combustible gases in mines. He also invented a cold cathode tube that could amplify the small signal generated by the detection mechanism to a strength sufficient to activate an alarm. Ionization smoke detectors were first sold in the United States in 1951. They were used only in major commercial and industrial facilities in the next several years due to their large size and cost. In 1955, simple home fire detectors for homes were developed, detecting high temperatures. The United States Atomic Energy Commission granted the first license to distribute smoke detectors using radioactive material in 1963. The first low-cost smoke detector for domestic use was developed by Dwayne D. Pearsall in 1965, an individual replaceable battery-powered unit that could be easily installed. The Smoke Guard 700 was a beehive-shaped, strong fire-resistant steel unit. The company began mass-producing these units in 1975. Studies in the 1960s determined that smoke detectors respond to fires much faster than heat detectors. The first single-station smoke detector was invented in 1970 and made public the next year. It was an ionization detector powered by a single 9-volt battery. They cost about $125 and sold at a rate of a few $100,000 per year. Several technological developments occurred between 1971 and 1976, including the replacement of cold cathode tubes with solid-state circuitry, which greatly reduced the detector's sizes and made it possible to monitor battery life. The previous alarm horns, which required specialty batteries, were replaced with horns that were more energy efficient. enabling the use of commonly available sizes of batteries. These detectors could also function with smaller amounts of radioactive source material, and the sensing chamber and smoke detector enclosure were redesigned for more effective operation. The rechargeable batteries were often replaced by a pair of AA batteries along with a plastic shell encasing the detector. The 10-year lithium battery-powered smoke alarm was introduced in 1995. The optical smoke detector was invented Donald Steele and Robert N. Mark of Electro-Signal and patented in 1972. Design. Ionization. An ionization smoke detector uses a radioisotope, typically americium-241, to ionize air. A difference due to smoke is detected and an alarm is generated. Ionization detectors are more sensitive to the flaming stage of fires than optical detectors, while optical detectors are more sensitive to fires in the early smoldering stage. The smoke detector has two ionization chambers, one open to the air, and a reference chamber which does not allow the entry of particles. The radioactive source emits alpha particles into both chambers, which ionizes some air molecules. There is a potential difference between pairs of electrodes in the chambers. The electrical charge on the ions allows an electric current to flow. The currents in both chambers should be the same as they are equally affected by air pressure, temperature, and the aging of the source. If any smoke particles enter the open chamber, some of the ions will attach to the particles and not be available to carry the current in that chamber. An electronic circuit detects that a current difference has developed between the open and sealed chambers, and sounds the alarm. The circuitry also monitors the battery used to supply or backup power, and sounds an intermittent warning when it nears exhaustion. A user-operated test button simulates an imbalance between the ionization chambers, and sounds the alarm if and only if power supply, electronics, and alarm device are functional. The current draw of an ionization smoke detector is low enough for a small battery used as sole or backup power supply to be able to provide power for months or years without the need for undamaged external wiring. Ionization smoke detectors are usually cheaper to manufacture than optical detectors. They may be more prone to false alarms triggered by non-hazardous events than photoelectric detectors, and have been found to be much slower to respond to typical house fires. Americium-241 is an alpha emitter with a half-life of 432.6 years. Alpha particle radiation, as opposed to beta and gamma radiation, is used for two additional reasons. Alpha particles have high ionization, so sufficient air particles will be ionized for the current to exist, and they have low penetrative power, meaning they will be stopped safely by the plastic of the smoke detector or the air. About 1% of the emitted radioactive energy of 241 am is gamma radiation. The amount of elemental americium-241 is small enough to be exempt from the regulations applied to larger sources. It includes about 37 kilobecquerels or 1 micro-Ci of radioactive element americium-241, corresponding to about 0.3 micrograms of the isotope. This provides sufficient ion current to detect smoke, while producing a very low level of radiation outside the device. The americium-241 in ionizing smoke detectors poses a potential environmental hazard. Disposal regulations and recommendations for smoke detectors vary from region to region. Some European countries, like France, and some U.S. states and municipalities have banned the use of domestic ionic smoke alarms. Specific activity is 3.5 Ci per gram. Photoelectric. A photoelectric smoke detector or optical smoke detector contains a source of infrared, visible, or ultraviolet light, a lens, and a photoelectric receiver. In spot-type detectors, all of these components are arranged inside a chamber where air, which may contain smoke from a nearby fire, flows. In large open areas such as atria and auditoriums, optical beam or projected beam smoke detectors are used instead of a chamber within the unit. A wall-mounted unit emits a beam of infrared or ultraviolet light which is either received and processed by a separate device, or reflected back to the receiver by a reflector. In some types, particularly optical beam types, the light emitted by the light source passes through the air being tested and reaches the photosensor. The received light intensity will be reduced by absorption due to smoke, airborne dust. In other types, typically chamber types, the light is not directed at the sensor, which is not illuminated in the absence of particles. If the air in the chamber contains particles, the light is scattered and some of it reaches the sensor, triggering the alarm. According to the National Fire Protection Association, photoelectric smoke detection is generally more responsive to fires that begin with a long period of smoldering. Studies by Texas A&M and the NFPA cited by the city of Palo Alto, California state, photoelectric alarms react slower to rapidly growing fires than ionization alarms, but laboratory and field tests have shown that photoelectric smoke alarms provide adequate warning for all types of fires and have been shown to be far less likely to be deactivated by occupants. Although photoelectric alarms are highly effective at detecting smoldering fires and do provide adequate protection from flaming fires, fire safety experts and the National Fire Protection Agency recommend installing what are called combination alarms, which are alarms that either detect both heat and smoke, or use both the ionization and photoelectric processes. Some combination alarms may include a carbon monoxide detection capability. The type and sensitivity of light source and photoelectric sensor, and type of smoke chamber differ between manufacturers. Carbon monoxide and carbon dioxide detection. Carbon monoxide sensors detect potentially fatal concentrations of carbon monoxide gas, which may build up due to faulty ventilation where there are combustion appliances such as heaters and cookers. Although there is no uncontrolled fire out with the appliance, high levels of carbon dioxide may indicate a fire, and can be detected by a carbon dioxide sensor. Such sensors are often used to measure levels of CO2 which may be undesirable but not indicative of a fire. This type of sensor can also be used to detect and warn of the much higher levels generated by a fire. One manufacturer says that detectors based on CO2 levels are the fastest fire indicators, and also, unlike ionization and optical detectors, detect fires that do not generate smoke, such as those fueled by alcohol or gasoline. CO2 fire detectors are not susceptible to false alarms due to particles, making them particularly suitable for use in dusty and dirty environments. Performance differences. A presentation by Siemens and the Canadian Fire Alarm Association reports the ionization detector is best at detecting incipient stage fires with invisibly small particles, fast flaming fires with smaller 0.01–0.4 micron particles, and dark or black smoke, while more modern photoelectric detectors are best at detecting slow smoldering fires with larger 0.4–10.0 micron particles, and light-colored white, gray smoke. Photoelectric smoke detectors respond faster to fire in its early, smoldering stage. The smoke from the smoldering stage of a fire is typically made up of large combustion particles, between 0.3 and 10.0 micrometers. Ionization smoke detectors respond faster in the flaming stage of a fire. The smoke from the flaming stage of a fire is typically made up of microscopic combustion particles, between 0.01 and 0.3 micrometers. Also, ionization detectors are weaker in high airflow environments, and because of this, The photoelectric smoke detector is more reliable for detecting smoke in both the smoldering and flaming stages of a fire. In June 2006, the Australasian Fire and Emergency Service Authorities Council, the peak representative body for all Australian and New Zealand fire departments, published an official report. Position on smoke alarms in residential accommodation. Clause 3.0 states, ionization smoke alarms may not operate in time to alert occupants early enough to escape from smoldering fires. In August 2008, the International Association of Firefighters passed a resolution recommending the use of photoelectric smoke alarms, saying that changing to photoelectric alarms will drastically reduce the loss of life among citizens and firefighters. In May 2011, the Fire Protection Association of Australia's official position on smoke alarms stated, Fire Prevention Association Australia considers that all residential buildings should be fitted with photoelectric smoke alarms. In December 2011, the Volunteer Firefighters Association of Australia published a World Fire Safety Foundation report. Ionization smoke alarms are deadly, citing research outlining substantial performance differences between ionization and photoelectric technology. In November 2013, the Ohio Fire Chiefs Association published an official position paper supporting the use of photoelectric technology in Ohio in residences. The OFCA's position states, in the interest of public safety and to protect the public from the deadly effects of smoke and fire, the Ohio Fire Chiefs Association endorses the use of photoelectric smoke alarms in both new construction and when replacing old smoke alarms or purchasing new alarms. We recommend photoelectric smoke alarms. In June 2014, tests by the Northeastern Ohio Fire Prevention Association on residential smoke alarms were broadcast on the ABC's Good Morning America program. The NEOFPA tests showed ionization smoke alarms failing to activate in the early, smoldering stage of fire. The combination ionization photoelectric alarms failed to activate until an average of over 20 minutes after the standalone photoelectric smoke alarms. This vindicated the June 2006 official position of the Australasian Fire and Emergency Service Authorities Council and the October 2008 official position of the International Association of Firefighters. Both AFAC and the IAFF recommend photoelectric smoke alarms, but not combination ionization photoelectric smoke alarms. According to fire tests conformant to N54, the CO2 cloud from open fire can usually be detected before particulate. Due to the varying levels of detection capabilities between detector types, manufacturers have designed multi-criteria devices which cross-reference the separate signals to both rule out false alarms and improve response times to real fires. Obscuration is a unit of measurement that has become the standard way of specifying smoke detector sensitivity. Obscuration is the effect that smoke has on reducing sensor visibility. Expressed in % obscuration per unit length, higher concentrations of smoke result in higher obscuration levels. Interconnected smoke detector systems. Smoke detectors may be interconnected, either as part of an alarm system, or simply as grouped alarms in a domestic situation. Interconnected smoke detectors are either conventional or analog addressable, and are connected to security alarm or fire alarm systems controlled by fire alarm control panels. These are the most common type of detector, and may be significantly more expensive than single-station battery-operated smoke alarms. They are used in most commercial and industrial facilities and other places such as ships and trains, but are also part of some security alarm systems in homes. These detectors don't need to have built-in alarms, as alarm systems can be controlled by the connected FACP, which will set off relevant alarms, and can also implement complex functions such as a staged evacuation. Conventional. The word conventional is slang used to distinguish the method used to communicate with the control unit in newer addressable systems. So-called conventional detectors are smoke detectors used in older interconnected systems and resemble electrical switches in their information capacity. These detectors are connected in parallel to the signaling path so that the current flow is monitored to indicate a closure of the circuit path by any connected detector when smoke or other similar environmental stimulus sufficiently influences any detector. The resulting increase in current flow is interpreted and processed by the control unit as a confirmation of the presence of smoke, and a fire alarm signal is generated. In a conventional system, 32 smoke detectors are typically wired together in each zone, and a single fire alarm control panel usually monitors a number of zones which can be arranged to correspond to different areas of a building. In the event of a fire, the control panel is able to identify which zone or zones contain the detector or detectors in alarm, but cannot identify which individual detector or detectors are in a state of alarm. Addressable. An analog addressable system gives each detector an individual number or address. Addressable systems allow the exact location of an alarm to be plotted on the FACP. In certain systems, a graphical representation of the building is provided on the screen of the FACP, which shows the locations of all of the detectors in the building, while in others the address and location of the detector or detectors in alarm are simply indicated. Analog addressable systems are usually more expensive than conventional non-addressable systems, and offer extra options, including a custom level of sensitivity which can determine the amount of smoke in a given area, and contamination detection from the FACP that allows determination of a wide range of faults in detection capabilities of smoke detectors. Detectors become contaminated usually as a result of the buildup of atmospheric particulates in the detectors being circulated by the heating in air conditioning systems in buildings. Other causes include carpentry, sanding, painting, and smoke. In the event of a fire, panels can also be interconnected to control a very large number of detectors in multiple buildings. This is most commonly used in hospitals, universities, resorts and other large centers or institutions.